Now the symmetric group Sn is a group, so it's useful to look at how multiplication works. And in this group, it's also very convenient sometimes to represent all of the elements as matrices. So let's look at those two issues. Let's define the matrix of W1 through Wn in the nth symmetric group to be the matrix that has ones in positions I, Wi for all I and zeros elsewhere. So for example, if W equals 4, 1, 2, 3, then the matrix, let's say P of W, is we have a 1 in position 4, a 1 in position 1, a 1 in position 2, and a 1 in position 3. Now, multiplication of generators is consistent with multiplication of matrices defined this way. So for example, if we look at S1, S2, S1 times S2, S1, so to multiply we would just write the generators in this order. And maybe look at what we can reduce and make shorter using the relations we know. So we know that S2, S1, S2 is the same as S1, S2, S1 because of the braid relation. That is, the indices are exactly 1 apart, so we can swap this expression with that expression. And then we know that any generator squared is the identity, so that makes this the identity and that the identity. So we're just left with S2. So this first statement is correct, but that expression in terms of generator simply isn't the shortest, so we might prefer to write it as the shortest possible expression in generators, little s2. And we said that little s1, little s2 has one line notation obtained by applying this to the word 1, 2, 3. So that's S1 of 1, 3, 2, which is 3, 1, 2. And then if we look at the matrices for S1 and S2, we've got, this is the S1 matrix. Let me write it bigger. And then the S2 matrix is this. So 2, 1, 3, 1, 3, 2, because S1 swaps the things it sees in positions 1 and 2, and S2 swaps the things that it sees in positions 2 and 3. Then if we multiply, we get 0, 0, 1, 1, 0, 0, 0, 1, 0. And this is the matrix of 3, 1, 2. I meant 0, 1, 0. So it works the same as the generators applied to a word as functions. Also, if we put up, let's see, the 4, 1, 3, 2 matrix, 1 in position 4, position 1, position 3, position 2. I don't think that's what I had before, but if we apply this to the vector 1, 2, 3, 4 and multiply, we get 4, 1, 3, 2. So applying these generators to word is the same as multiplying a matrix by the vector 1, 2, 3, 4. And then if we have permutations written in two-line notation, which is one-line notation with 1 through n written above, we can perform multiplication by, well, we'll do an example. 1, 2, 1, 3, 2, 1, I'm sorry, the top word is always 1, 2, 3 in order. 1, 2, 3, 2, 1, 3 times 1, 2, 3, 1, 3, 2. So we're multiplying S1 times S2. And we want to get 3, 1, 2. So we follow 1 from 2 and then 2 to 3 and say that 1 goes to 3. So 1 to 2 and then find the 2 over here and then see where that goes. Then 2 to 1 and follow the 1 over here and see where that goes. 2 goes to 1, 1 goes to 1. So 2 goes to 1, and then 3 goes to 3, and 3 goes to 2. So we get 3, 1, 2. So we just follow the letters 1 through n to where they go in the first permutation, then where that letter goes in the second permutation, and then that's the product. And then if we do this with generating functions, well, we pretty much have already, but I will do it again anyway. So we just glue together, follow the line straight across, and we see that 1 goes to 3, 2 goes to 1, 3 goes to 2, and that's essentially how we defined one-line notation in the first place. And maybe it'll be worth it to do an example with an expression that's not reduced. So we said that S1, S2, S1, S2, S1 reduces to just S2, because this inner word with 3 letters here becomes S1, S2, S1, then we've got cancellation of S1s. So if we do that with wiring diagrams, then we see S1, S2, S1, S2, S1. Has a wire that sends 1 to 1, 2 to 3, and 3 to 2. So we get 1, 3, 2. Which is not consistent with what we did before because that's a different problem. 1, 3, 2 is S2. So that's consistent with multiplication of the generators up here. The end.